Welcome to second lesson of this series about unit, dimension and measurement, and in this lesson we discuss about dimension analysis. In the following way, first we understand what is meant by dimensions. After that we learn about how to write a dimension formula and use of dimension analysis with examples. When a physical quantity is expressed in terms of physical quantity, the base quantity expressed in terms it is written as the product of different power of the base quantities. The power of a base quantity that enters into the expression is called the dimension of the quantity in that base quantity. So, the dimensions of density are 1 in mass and -3 in length, and dimensions of all other fundamental quantities in this case are 0. For convenience, the fundamental quantities are represented by one letter symbols. Generally, mass is denoted by m, length by L, time by T, and electric current by I. The thermodynamic temperature, the amount of substance and the luminous intensity are denoted by the symbol of their units, Kelvin, mole and candela respectively. And a physical quantity that is expressed in terms of the base quantities is enclosed in square brackets. So, the density written as density is equal to mLT to the power -3 in square brackets. Such expression generally called dimensional formula. The use of dimension analysis. From dimension analysis, we can check the use any physical equation whether the equation is correct or not. We can convert a physical quantity from one unit system to another unit system, and we can deduce the relation between physical quantities. We will discuss all the three one by one. First, checking whether a equation is correct or not. In physics, every physical equation should be dimensionally balanced. That means the dimension of each term on both sides of an equation must be same. Let us check. Consider a equation x is equal to ut plus half at square, where x is the distance travelled by a particle in time t, which start at a speed u and has an acceleration a along the direction of motion. So, the dimension of x is equal to L. The dimension of ut is equal to velocity into time is equal to length by time into time. Time cancel each other, then it is equal to length is equal to L. The dimension of half at square is equal to velocity by time into time square is equal to length by time square into time square, then is equal to length is equal to L. So you can see that the dimension of each term on both sides is same. So equation is correct. In this way, we can check any equation whether it is correct or not. Conversion of a physical quantity from one unit system to another unit system. Dimension can be useful in finding the conversion factor for the unit of a derived physical quantity from one unit system to another. Consider an example. The unit of force in SI unit system is Newton and in CGS system is Dyne. Suppose we want to find the value of 1 Newton is equal to how much Dyne. We know the dimension of force F is equal to mLT to the power -2, and in SI system unit of mass is equal to 1 kg, unit of length is equal to 1 meter, unit of time is equal to 1 second. So we can write from the dimension of force 1 Newton is equal to 1 kg into 1 meter into 1 second to the power minus 2. And in CGS system, unit of mass is equal to 1 gram, unit of length is equal to 1 centimeter, unit of time is equal to 1 second. Again, we can write from dimension of force 1 dyne is equal to 1 gram into 1 centimeter into 1 second to the power minus 2. Then the ratio of 1 Newton by 1 dyne is equal to 1 kg by 1 gram into 1 meter by 1 centimeter into 1 second by 1 second whole to the power minus 2. We know 1 kg is equal to 10 to the power 3 gram and 1 meter is equal to 10 to the power 2 centimeter. So that is equal to 10 to the power 3 into 10 to the power 2 is equal to 10 to the power 5. Therefore, 1 Newton is equal to 10 to the power 5 dyne. So, anyone can find out the conversion factor for any derived quantity if the dimensional formula
deducing
of the
relation
quantity
among the physical quantities. If we know the quantities on which a particular physical quantity depends, then we can find the formula which shows the relation among those physical quantities. Suppose we want to derive the expression for the centripetal force F acting on a particle moving uniformly in a circle may depends on mass m, velocity v and radius of the circle r. We assume that the dependency of the centripetal force on these quantities is of product type, that is F is equal to K into m to the power x into v to the power y into r to the power z, where k is a dimensionless constant and x, y and z are exponent which we want to evaluate. First, we have to find the dimension of each quantities. We know dimension of force F is equal to ml t to the power minus 2, dimension of mass m is equal to capital M, dimension of velocity v is equal to L t to the power minus 1, dimension of radius r is equal to L. Now taking the dimensions of both sides in that equation, we get ml t to the power minus 2 is equal to m to the power x, L t to the power minus 1 whole to the power y, L to the power z is equal to m to the power x, L to the power y plus z and t to the power minus y. Since the dimension on both sides must be identical, so we get x is equal to 1, y is equal to 2 and y plus z is equal to 1. That implies that z is equal to 1 minus y, and putting the value of y we get is equal to minus 1. So the final values are x is equal to 1, y is equal to 2 and z is equal to minus 1. Putting these values in this equation, we get f is equal to k m v square r to the power minus 1, and by rearranging k into m v square by r, we cannot determine the value of k from the dimension analysis. By experiment, k is equal to 1. So the centripetal force is directly proportional to mass of the particle and its square of velocity and inversely proportional to radius of the circle.